Good afternoon. We're glad you're here at the FRAC conference this afternoon, and we're going to give a talk this afternoon about protecting the parent well. This is one of the hottest topics in the industry right now, and it's a combination of knowing your reservoir, understanding the mechanics of what you're doing, and we are a chemistry company. So that's why we are here talking about the role of chemistry in protecting the well. Just to give you a little bit of outline of where we're going to go, executive summary, some terminology, published industry findings, our hypothesis applied to the Permian Basin, and the role of the fluid chemistry and what it plays. So when you look at where our hypothesis is going, combining both the physics of what you're doing mechanically with the reservoir, with the chemistry, hydraulic fracture complexity itself does not dictate a positive or negative interaction. Now, that's a little contrary to what sometimes is popularly believed out there, but we're going to back that up with industry findings and actual client use of chemistry and the success that they had. Chemistry can be customized and used to both mitigate the damage in the primary well and to remediate near wellbore damage. So that in one hand is about making sure it doesn't happen, and then if it does happen, how do you go back and how are you able to fix it? And that fluid chemistry is tailored for the reservoir characteristics, the mineralogy you're dealing with, for the spacing that you're dealing with, and the amount of fluid, the timing for what you're doing. And if this goes out again, we're just going to wing it, but let's hope it stays strong. So everybody talks about child wells. They talk about the parent wells. So I'm going to try to actually, and I'm doing a promotion here for Dana Shea and George King, who have a wonderful paper out there going, you know what, instead of talking about all these family dysfunctional issues, let's actually call it primary infill wells, fracture-driven interactions instead of all the bashing and everything else. Keep it a little more professional. So I'm going to try to use those terms today, just kind of setting the stage for that. Frac-driven interaction concept. You got your primary well, and then you go and you put your infill well, and the natural fracs in this case are in direct communication, and that means that if you're not doing the right prevention, you're going to be having pressure coming across, you're going to be having fluids coming across, you could have proppant coming across, and you can very easily have a less productive infill well, and you can also, in many cases, unfortunately, absolutely kill out your primary well. And that's what you don't want to have happen. So there's multiple ways to look at that. Whenever you're looking at what frac-driven interactions can do, damage well integrity, the interconnected frac works don't always provide the fluid pathways. Sometimes it is pressure, but in either way, that is an interaction that can be very positive or negative. But the one thing that we don't talk about often is that frac-driven interactions can be positive. And whenever we look at some of the other papers in a second, we will actually be able to show that, and that ties into the pore pressure and the formation pressure, whether it's overpressured or whether it's actually very depleted. So primary wells and formations that are naturally overpressured have a much reduced tendency of having negative frac-driven interactions as opposed to very depleted reservoirs. And the total production from primary and infill combo many times is lower than what you would expect from 1+1. 1+1 rarely these days, especially if they're too close, equals 2. 1+1, unfortunately, a lot of time only equals about 1.5 or less. So whenever you think about the role of pore pressure, you look on this side and you've got all of the red, and this is your primary well, very depleted, lower reservoir pressure going on there. You bring in the infill well, and of course, what does it want to do? All of that energy wants to go to the lowest place. It wants to go toward that depleted well. So not only are you interacting and bashing this one, but you're reducing the efficiency of the well on the other side, the higher pressure side, because it doesn't have any power left to go there. All of the energy is going into the offset well. So whenever you have a higher reservoir pressure, you can actually have a much more productive primary well ongoing, but then your infill well is also much more productive as well. So how do you take a depleted system and then be able to keep it from being bashed by one or the other if you don't have the luxury of having a higher reservoir pressure. That's where the process that we're going to talk about, well, let's go through this first. So whenever we talk about, this is a paper by Schlumberger several years ago. It was a great paper, and it talked about in these different basins both positive and negative frac-driven interactions. And when you look at the pore pressures that are going through each of these, the higher the basin pore pressure on average, you're actually seeing a higher propensity to be able to have a chance of having positive frac-driven interactions as opposed to negative, or having a lower percentage of negative frac-driven interactions. So if you're going through the pore pressure hypothesis and you look at the Delaware Basin and you're looking at a 3D pore pressure, this was all from different mudlogging, IPs, ISIPs, DFITs. You see a higher pressure region here, and you see that modeled no matter which way they were actually measuring that. And this is from a UTEC paper several years ago. So there you are, your higher pressure areas you would actually expect to be able to have fewer negative, or be able to minimize the negativity of those frac-driven interactions in those areas. But that also means that if you're in other areas of acreage, you might have a higher chance of having a problem with that. If you look over on the Midland Basin, you see that your highest pressure in that area is going to be in this area, and then it goes out from there. So with that, you would actually expect that the overpressured areas would see mostly positive FDI interactions. The shallower the interval, the less pressure, you're going to have more of a negative interaction. And when you're looking at the Delaware Wolfcamp significantly over the Midland, it's more overpressured than the Midland side, so you would expect a difference between one side of the basin than you would for the other. So that's a lot of talk about things that have nothing to do that I've said with chemistry. And I work for a chemistry company. So whenever you talk about where does the role of chemistry come in with setting the stage for how do you deal with lower pore pressures, how do you deal with the reservoir, and what does chemistry role play in all that? It absolutely does. Mitigation strategy. If you want to be able to increase your lateral spacing, reduce the infill treatment size, these are all very valid strategies, and fluid chemistry plays a part in all of those. But there was a paper that we were very much involved with BHP, and they presented that. It was SPE 1917-12. I would love for y'all to go look it up. Nowhere in that paper do they say the word Flowtech, and I want to call that out. But they do say in that paper, they talk about the methodology that they use to be able to very effectively prevent frac hits. And they talk in there about a nanosurfactant, and that they had the most success when they've had a physical regimen that they did in conjunction with chemistry. SPE has very, very rigid rules, and for good reasons, about why you're not supposed to use those kind of papers as commercials. But I'm telling you, that's us. And it was a process of conjunction with the physicality of what they did, along with what they did for the chemistry. So what is the chemistry doing? And which type of chemistry are we talking about? I'm talking about complex nanofluids, and that's a trade name in the industry for a combination of surfactant and solvent. And we would love to tell you about it. We've got all kinds of brochures about it. It's a science that is a whole technology platform unto itself, and it both reduces capillary pressure and helps solvate and change impacting wettability to more neutral wettability. So one of the biggest issues when you think about frac-driven interactions and you think about fluids coming across, you're thinking about things that can happen like phase trapping. And whenever you have the right surfactants and you have the right solvent in there impacting wettability, you can be increasing the effective permeability. You can be able to change the how connected those pathways are, not from an actual, you're not changing the rock, but it's about like effective fracture length, how effectively they're connected across the formation. So whenever you're looking at changing the mobility package, you've got fluid system designs that are affecting connectivity. Those are your FRs, your base fluid. And then whenever you're talking about the complex nanofluid and the surfactant and the solvent components, Together, they're changing the effective permeability of your reservoir. So how does that apply to our frac-driven interactions? Well, one last slide before I get there. So whenever we talk about complex nanofluids, I said it was solvent and multiple types of surfactant here. The solvent that we use, if you've ever seen a lot of our brochures, we have an orange Mohawk. That's because we actually use limonene. The limonene comes from the rind of oranges. It's a very green solvent, but we use it because it's very effective at solvating and mobilizing everything from asphaltenes and paraffins, but also being able to lower surface tension even in gas well formations. When you combine the surfactants with the solvent, they're able to make nano-sized droplets carry farther with the fluids into the formation, touch more of the surface area of the formation. You can use them in stimulations. We use them in water floods. We use them in enhanced recovery. But we also very much use them in remediation on frac hit wells and for loading up primary wells as preventative, as a prevention whenever you're doing infill wells. So this is an example that we published with Apache several years ago. This is where you had a parent well that had been bashed. And they were going, what the heck can we do about it? So if you look at the oil and gas curve here, and then all of a sudden, guess what? There's that child well. It comes in, and it just crashed it. And then you're able to see that it is slowly trying to be the little engine that could, and it's chugging along and is trying to come back. Whenever we came in conjunction with a very tailored chemistry protocol that included CNF and included some materials to be able to account for clays, because this was actually in the mid-con with their formation, all of a sudden everything pops back up to the original trajectory, and they were able to eliminate all that wedge of lost production. For a very small investment in the chemistry, for what they did, they were able to recover significant amount of productivity in that well. The only thing I wish they would have done different was I wish they would have done it sooner so they could have had a bigger part of the wedge. So that would be a remediation in a frac-driven interaction. And here's the paper where we were talking about that was in conjunction with BAP that they actually doesn't say Flowtech, but it's really Flowtech. So whenever you look at what they did, this was in the Eagle Ford. They started trying a lot of different things. They started going, okay, we're just going to leave the parent well on, and we're going to frac the infill well, and while the primary wells, we're just going to let it keep producing. We're going to see how that does. Well, what that did was that actually resulted in about a negative 40% of productivity for that well. So then they started playing around with, well, let's preload the primary well, and they did it with a small volume. Okay, they still were somewhere in the negative 40%. Then they also tried several different defensive fracturing type methodologies, and what finally, on a consistent level, gave them not only a negative 40, but a positive 20% in that area, was they did a large preload. Now, this is a graph we lifted from that paper, and it doesn't say anything about chemistry here, but they actually put complex nanofluids in that volume that they were preloading. And it was a combination of both the physics and the chemistry, because what they did was they were very careful to preload the parent well just up until underneath the frac gradient they were doing before they were doing the infill well. And they were doing that at a very slow rate of penetration into the formation. So from a physics standpoint, you're thinking, okay, they literally took that balloon around the parent well, they filled it up with a large volume of water, and made it so that when the infill well was being fracked, the pressure wave came across, but the fluid wave couldn't go anywhere because the balloon was too tight. So everything had to come across and it stopped. The problem, the good news is that was a large volume of fluid they just put on the primary well. But with the right chemistry in it, instead of it causing phase trapping and not being able to unload, they were then able to immediately turn the primary well on, use the pressure wave from the infill well, and be able to unload all of that fluid and not have the primary well the hit. After all of that was being unloaded, then you turn on the infill well, and both wells were then giving you 1 + 1 is 2. They saw that over and over. Management said, I don't want to spend money on chemistry. Take the chemistry out. They tried that. Didn't work nearly as well at all. Don't want to say percentages, but they ended up putting chemistry back in and they taught themselves a lesson. Chemistry has a role in being able to mitigate phase trapping, all of that. But on top of that, you were coating the formation with surfactant and solvent that was then able to help mobilize and move things through that formation and have contact and resonance time that you would dream of for having a chemical soak on your formation. So it was twofold. So looking at the infill production, so we're a lot of times if they were parent, they were doing fraction flow, and you were getting a negative 15 off of what you would have as your type curve. When they were doing the large preload, you were actually hitting your type curves for the infill well. Everybody wins. It's a win-win across the board. So, what's the lesson? Include a complex, include a chemical solvent and surfactant package whenever you're doing this process. They then went and took that and started transferring those lessons learned to their Permian reservoir in the Delaware Basin. They only had a few days at that point, as quite honestly, BHP got sold. So they didn't have access to that acreage to be able to play around with it. But what you're seeing here is this 10,000 barrel preload that's up here. Those are consistently above, as opposed to all the shut-ins that are completely down here. And frac and flow is certainly not doing a great job. So they were proving to themselves in a very different basin, but with maybe different volumes, being very reservoir-centric about rate of penetration of whether they were loading up the formation, but also getting very, very positive results. Again, so lesson learned, we would say include a chemical solvent surfactant package. Both the physics, the mechanical nature of what you're doing, coupled with the chemistry, gave you the best response. So in summary for today, fracture complexity by itself does not dictate positive or negative frac-driven interactions. Tailored chemistry can be used in the primary wells and to both mitigate and to remediate, and that all needs to be customized for the mineralogy and for the pore pressure, for all the different reservoir metrics that you've got going on there, and that it may be statistically predictable for what you would expect, so that you can have positive or negative with knowledge ahead of time to be able to mitigate it as much as possible. Thank you for your attention today, and we would love to take any questions if you have them. Thanks.